Hello and welcome back to Data Science CastNet. In today's video I thought we'd take a look at this new method from Google and UIUC, ZipLoRA any subject in any style by effectively merging LoRAs. And so they claim that you can take some user-provided images of some subject and one or more images of a style and then create really high-fidelity images that capture both of those components a lot better than any existing techniques. And so rather than diving straight into the paper, I thought what we'll do instead is we'll go into the background. What are LoRAs? Why is merging them hard? What is the problem that this paper is trying to solve? We'll try and solve that ourselves, and then we'll look at the technique and the solution that the paper came up with, as well as what an implementation might look like, and see how that effectively produces this higher quality new approach. So most of the video is going to be in this notebook, which I'll share alongside the video. And we're going to be working with a couple of demo LoRAs that I've trained. So first up, if you're in the Stable Diffusion world, you might know a LoRA just as something like a model, right? It's been fine-tuned on a particular subject or style, and it's a way to then share that with others so that they can access that same style. And it's much smaller than the base model. So this is like a lower size way to share some customization of a model. And that's very much what they are from a practical sense. So for example, I have here 5 images. These are just kind of marginalia from my Nature Journal notebooks. Quickly snap some photos. And those 5 images have been used to train a LoRA that I'm calling the Nature Journal style LoRA. And then if you load this LoRA, you can now generate a different subject or whatever prompt you like in that style, and you'll get that same sketchy watercolor, bad cell phone picture in a spiral-bound notebook aesthetic, right? So it's really captured that essence really well. And if you're curious how I trained these, just for this demo, I am using the new Train Dreambooth LoRA SDXL script from the Diffusers team. And so we're going to pass in, let's find the style one. This is my base model. This is what I'd like to call the new LoRA. This is a folder that contains those images. This is the prompt that I would use, and this is a validation prompt that I can use just to check that it's working. And so when we run this, we specify things like how many steps to do and so on. What we're going to end up with is something like this. So now we get a nice repository on the Hugging Face Hub. You can see some examples here with that validation prompt. None of the training images are snails. Likewise, you can try the little inference widget, the blue wildflower. It seems to be doing the job. So likewise, I've done a subject LoRA using this set of images, and now these aren't my images. These were taken by one of the authors of the ZipLoRA paper, who's also the author of the Dreambooth paper where this image was first used, this little doggo here. And it's a good test for checking that it's keeping to the subject identity really well. You see it's this little plushie, it's got this little neckerchief, it's got blue eyes. So we can check to see whether our LoRA is faithful to that or not. So here we load that LoRA in. This is the trigger word that I use, an SPU dog, wearing a top hat, sitting up, and you see we get the dog wearing a top hat. It's kind of stuck in the same pose that it always is. And if we go to the training run for this LoRA, these are the images generated right at the start of training. And if we look through after 250 steps or 255 steps, we've mostly got the general look of the object, although not perfectly. After 500 steps, we're now very much seeing the same pose, and in fact, even though our prompt is talking about on a bed, the backgrounds are starting to look more like the background of one of the images. By 750 steps, even more so, these don't look like beds at all, and we seem to be very fixed, just recreating the same sort of subset of poses. So after 1,000 steps of training, this LoRA is, I would say, a little bit overfit, right? It's going to struggle to follow my other prompts too well, but it still seems to work, and this is a really good test. Because as we'll see, depending on how much training you did on your LoRA, how powerfully it's influenced the model, what size of change it's made to the weights, that's going to have a drastic effect on how easy it is to mix and match different LoRAs to get the results that we want. Okay, so what if we want to use those two LoRAs together? I've trained one for style, I've trained one for the object. I'd now like to combine them so that I can get my object in my style. Well, the official way to do this from Hugging Face is to load the LoRAs one at a time and then fuse them in. And we'll look at how this works just now, but this is going to take, instead of having the separate adapter on the side, which is what the LoRA is, low rank adapter, It's going to merge those into the main weights of the diffusion model, and then you can do this multiple times to kind of additively stack the different effects. And we can do that with some scaling. And now I'm prompting for an SPU dog in SN style, and yet I just get a photo that looks kind of like the dog. Remember I said this dog LoRa is a little bit overtrained, but the good news is that there's the scaling factor. All right, so we can choose whether to take the full delta from the LoRa, or only half of that, or 5 times that. We can emphasize different parts, and so I can downweight the object LoRa scale, increase the scale for the style. Now I get a dog in the very sketchy watercolor style, but it's just a dog. It's maybe got a little red collar, definitely not that wolf plushie. And so you can tweak it at this. You can experiment and find something that sort of works. Here's one that looks a little bit better, but this is the problem, right? Because every combination of LoRas is going to require different scales for each. Some might be too strong, some might be too weak. The ways that you prompt them might mean that the pattern that the model was used to seeing during training is different, because you're now saying a dog in this style instead of just whatever the training prompt was. And so there's a lot of adjustment here, right? And this is a lot of manual work that we would like to avoid. Ideally, we wouldn't need to do any tuning, any scaling, any fiddling to be able to get our results. So that's where the paper comes in. So to think through how we might tackle this, it's worth looking at exactly how LoRas work in the first place, and then to start thinking like, how can we tinker with that machinery rather than just relying on, the Hugging Face fuse weights function. What if we can do that ourselves and try and figure out a way to kind of more intelligently combine these two ideas? Okay, so to start with, let's start by looking at what is a LoRa anyway. When I say, well, this is my LoRa that I've trained for this plushie, like, what is that? And what this is a stack of weights. So it has a state dict just like a model might in PyTorch. And these are all targeting components of the UNet. You can also train a LoRa adapter for the text encoder, but these are just for the UNet of the diffusion model pipeline. And so here, for example, UNet.downblocks, the first down block, attention 0, transformer block 0, attention. This attention block has 2K to V to Q and 2 out linear layers. And each of these is a 640 input and 640 output little linear layer, torch.nn.linear. And so the weight matrix of that is 640 by 640. Now, if we wanted, we could just train a new version of the UNet, a new set of weights, and then we could distribute that and say, here's my new set of weights, it knows what the plushie looks like. The problem is that's a large file size, that's a lot of parameters to handle, it takes a lot of memory during training, and so what LoRa does is it says, rather than training all 640 times 640 weights, we're only going to train a smaller subset. Specifically, we're going to train one set of weights that maps 640 dimensions down to some smaller rank. This could be 16 or 32, in this case it's 64. And another that goes from that 64 back up to 640. Right, so now instead of having 640 times 640, I have 640 times the rank, which is 64, times 2. I have a down and an up matrix. Right, and I have this for every linear layer that I'd like to update within the whole model. So I have the transformer blocks attention in out query. I have it for the res blocks, any MLPs anywhere in the chain, pretty much anywhere where there's a dimension by dimension matrix. We now have a D by rank and a rank by D set of LoRa adapters, right? And what we can do is we can either pass the data through first projecting it down to the rank and then back up, or we can expand those two matrices, the A and B, expand them through multiplying the two together to get a matrix that's the same size as the original weights. And what we're going to do when we talk about fusing is we're going to do this expansion. So I'm going to take my down and my up LoRas and multiply them together to get a 640 by 640 matrix of values, which is going to be a difference that I apply over the base weights. So I have my UNet, much bigger than the LoRa. It has a 640 by 640 matrix of weights in some layers, 2K projection. I'm going to create another matrix of that same shape by multiplying my two smaller LoRa matrices together. And I'm going to add the resulting 640 by 640 matrix on top of the base weights. Right? So we call that the delta. So to see this in action, let's generate with a fixed seed. Let's generate an image of our dog. And then we can check that our merging works the same. So here I'm loading the LoRa in just with the vanilla diffusers setup. Here we're going to manually try and do the same thing. So I have my pipeline loaded fresh, so it doesn't have the LoRa applied yet, it's the base pipeline. We're going to run through that whole state dict, and anywhere where there's a down part of the LoRa, I'm going to find the corresponding up LoRa. So I'm going to call these A and B, right? So this is the two matrices, 640 by 64 and 64 by 640, and I can multiply them together to get my delta W, right? This is the difference that I'm going to add to the base weights. Find the target layer, and then add to that target layer's weights this dW. Now some LoRas ship with a scaling factor, alpha. So you'll see when we load the state dict, we say state dict in alphas is pipeline.load LoRa. In this case, we don't need to worry about that because I trained these without that scaling. Okay, so this is not too crazy. I thought it would be useful to have this illustrative example here. Unfortunately, because people have been sharing LoRas in different formats with different naming conventions, some of them have unet.unet.arc, some of them have other tweaks, or they only target a subset of layers. The actual diffusers code is a lot more complex. But if you dig through that, you'll find that with multiple backends and lots of extra functions, at the bottom somewhere is going to be this operation where we take those two LoRa matrices, we multiply them together, and then we add those to the existing weights of that layer that we're targeting to fuse in the LoRa. And then if we generate with this, we now get exactly the same image using the same seed. So we know that this has worked in exactly the same way as the diffusers implementation. But yeah, this is just for illustration. Obviously, if you're trying to do this yourself, make sure that you support all of the extra parameters and so on. And I recommend just going with theirs. But now we know what's happening. And now we have a toy example that we can play with. Because the question becomes, okay, now that I know what's happening when I merge this in, how can I think of modifying that process to manage multiple LoRas together, right? And so I'm going to do a first pass where we load the weights of both LoRas, then we run through and we get the dW from the first one and the dW from the second one, and we just combine them with some scaling. Now this is more equivalent to the, again, the official diffuser's way of doing multiple LoRas, and we get a result where we're able to generate something that looks kind of like our plushie. It's got the red neckerchief, slightly different color coat, but we can mess with these scalings to affect that result, plus or minus, for example. Okay, but this is not the only way we can do it. There's other ways that you can think of to do that merging. So in the notebook here, what I've done is that same code as before, but now instead of just adding the two together, we can do things like create a mask that's one where one LoRa is higher than the other in terms of like absolute magnitude of that particular weight, 0 everywhere else, and then we use that mask to like selectively choose which one we're going to pick weights from, right? Doesn't necessarily make a huge amount of sense, but that's the kind of like formulas or tweaks, like, oh, how can we like get a better thing that keeps the best attributes of both but doesn't like push things too far where they both have the same like delta. You know, if this one says +1 here and the other one says +1 there too, not +2, and that's out of domain and it's all different. So you can start to mess with these effects. In this case, you'll see that picking whichever one is largest just gives us one way overweighted on the dog, but it does still know the other style. It's just that that's like hidden there and harder to extract. So that was maybe the wrong move. Maybe you could say, oh, well, I'll pick whichever one is, like I'll flip that mask, I'll use whichever one is smaller, or start to do like some cool, like maybe I'll square both of the deltas, then add them, and then take the square root of the results so that outliers don't affect it so much. I leave that to your creativity. But what you'll find when you mess around is it's very hard to come up with some general formula that works for lots of different LoRas, lots of different styles, because there needs to be this like fiddling, partly due to the fact that it's very unpredictable what happens when we combine these. Okay, so that's the context that we're operating with. So what's the solution that the ZipLoRA paper does? Because they show these beautiful results where we get Very, very good looking results in the right style, still very faithful to the object. What is the insight that led them to be able to do this? Well, there's a few things. The first is they try and dig into, okay, if we're looking at these weight matrices, what's going on there? Specifically those deltas that we generate from the LoRAs. They observe a few different things. One, those weight matrices are pretty sparse, right? Most of those elements are close to zero, and you can throw those ones that are close to zero away without really affecting the result. So the example here, they train a LoRa on this reference, and they use 100% of those weights. Then they throw away 80%, and they only keep 20%, and you can see it's still very faithful, very, very similar result. Even keeping 10% very, very similar. Okay, so that's a key insight, is like these matrices that we're adding here, they're not important values everywhere, they're only a few key values. Second thing that they observe is that highly aligned LoRa weights merge poorly. So when you've got columns of the weight matrices where the update from LoRa 1 and the update from LoRa 2 are very similar, they're kind of interfering with each other, and that's where a lot of the problem comes from. They say the information is not disentangled. Right, there's a high cosine similarity between these two sets of updates, and so the two stacked together is causing issues. And so that's going to be a problem. And they show the demo here, toy and a cartoon. If you do a direct merge, you don't end up with this in the style, you just end up with something that's like maybe a little bit of a flat shading version of that. And they show that the similarity, each step here is one column in the cross-attention delta, I guess. Yeah, you've got this fairly high cosine similarity, definitely non-zero similarity for the direct merge version. And they have a technique that somehow eliminates that. And when you do that, when you have these updates that aren't aligned, they are disentangled, suddenly you get exactly what you want. You get a nice flat cartoon illustration vector of the poop emoji. Okay, so that's their insight, is that they need to find a combined update that tries to keep as much of the individual LoRas as possible, but anywhere where the two are highly similar, we somehow like reduce that similarity. And I think we can go to, yeah, the training technique. And in combination with this, the paper doesn't release code. I think it's tricky for people at Google to release code. But fortunately, the author tweeted, hey, this is going to be fairly easy to implement. I intended to implement it. And by the time I finished Thanksgiving dinner, there was already a repository on GitHub. So congrats to the author. It was incredibly fast work throwing all of this together. And that means we have not just a pretty diagram, but we also actually have some training code. And so the essence of this method is we're going to take our two delta Ws, right, from our two different LoRas, and we've got one of these for each layer that we're updating. And then we're going to say, now I'd like to keep the functionality of this LoRa. That is, if I take an image of my subject and I add some noise to it and I try and denoise it, I'd like my predictions to look like they do when I just use that LoRa. Right, so I have a prediction when I have the combination, I have a prediction when I have just the LoRa for the content, and I can compare them to say, look, I want to make sure that I am still generating the same thing. I'm still generating the dog or the fluffy toy or the cat or whatever. Likewise for the style, I want my combined LoRa, when I say flowers in the style, I want it to generate flowers in that style. I want its predictions to match what I would get if I just used the style LoRa, right? So I have a loss that says, please try and make the predictions of the combination the same as the original LoRas. And then I add a loss that says, oh, and by the way, try and make it so that the columns of these W matrices are not very similar, right? And so if we go look at the code, you'll see that it sets up, it loads images and prompts for each of the two LoRas. It, let's go, picks a random time step, adds a certain amount of noise to the thing, and grabs the predictions. Give me the prediction when I have the merged weights with the concept, merged weights of the style, concept weights of the concept, style weights of the style. And so now we can start to compute these different components of the loss, right? How well does the prediction with the merged weights do at predicting the content image compared to just the one with just the contents LoRA. Likewise, how does the predictions based on the merge match the predictions based on just the style for the style prompt? And then the third loss, how well does the how similar are those weight matrices? If I go column by column through all of those W's and look at the cosine similarity, how similar are they? And they have this lambda parameter that can control like how much you weigh this part of the loss compared to the other two, and that gives us our final loss. So it is an optimization-based technique. It takes a while. You've got to do some training, and it's still not 100% clear like what the best parameters are for that. But if you run this script, and I've been running that in the terminal while I recorded this video, so hopefully it's finished. If you run this script, you end up with a final combined LoRa, which I'll run the one that I've just done. We can do a drum roll. Hopefully, when I generate with the prompt an SBU dog in SLN style, I get something that has, oops, I restarted the notebook, so I'm in the wrong directory. I get something that has the subject in the style that we want. So redo the drum roll, add some tension. This is killing me, live on camera. You get to see my real-time reactions. There we go, okay. And in this case it's failed. I'm going to double check that the pipeline knows the style that we want. I must confess I'm a little disappointed that it didn't quite work, but I think one of the main reasons is that this plushy LoRa that I've trained is very overtrained, so it seems like even this technique is not perfect. I'll double check this as a sanity check, but I think, yeah, okay, it can generate the style, so I obviously need to tweak the parameters, maybe train for longer, maybe, you know, penalize more the style loss or something like that. But okay, so maybe that's not the best demo of the results. We can look at the paper instead. They do this a lot more rigorously, and I think it would be nice to hear from the authors what settings they used. Maybe we can check the implementation here. It looks good to me, but maybe there's some nuances that we're missing. But yeah, they show with a single style, they're able to get really good stylizations training from just that single image. And then when they do their big grids, they show that their method, which is always going to be down the bottom row here, it does a really good job compared to all of the alternatives that have been proposed at really preserving the subject in the correct style, the subject in a nice flat cartoon style, the subject in a watercolor painting style. So you can go skim, there's tons and tons of results in the paper. I'll link the archive, give the archive link down below. And they show that you can also still do all the tricks that you normally can. You can change the prompt to specify what it should be doing, use other means of control. I'm sure you could combine this with things like control net and so on to enforce specific pose or specific depth or whatever. But yeah, really great, very thorough exploration of a way to get around this property where if we just naively merge two LoRAs by like averaging the weights or by merging them in one by one with a scale, it's very fiddly and it doesn't work super well. And their technique does seem, on the face of it, to solve this a lot. As you saw with my example, still isn't perfect. Partly maybe just because we still, if you just run the default training from the diffusers team, that's not a guarantee that that's always going to work well. In the Nature Journal style example, you can see here when it starts, it doesn't have the style at all. It's starting to get it after a few hundred steps, but yeah, it still gives a decent variety and it still works well. This is a snail, this is outside of its training data, so it's still able to generalize, whereas the wolf one, it's not able to show it on a bed, it's kind of like overfit. So that to me is like, okay, maybe I need to retrain that, but only use fewer steps or use a lower learning rate, maybe find some more diverse pictures of the subject. So there's still some nuance there. There's still some manual tweaking as much as the paper is trying to find like a parameter-free, like best case one-size-fits-all approach. But I still think it's really cool that we have that. And once you've done that work once you've trained, you found your scaling. So what they do is, I should mention how it works in the end is, this learns a set of what do they call it? They have a special name for it. A set of values that says how much of each column we're going to keep, or something along those lines. So there's a bunch of scaling factors which can then be merged in. In fact, it's probably in the code. Merger values, that's what they call it. Yeah, and so once we have those, we can then distribute a new LoRa based on those two ones that we'd like to combine. Or you could just tell your users, look, if you upload, you can imagine this being in like some sort of service, upload a style image, upload a photo that you want of your subject, we'll do the training behind the scenes, and we don't have to have someone sitting there manually tweaking sliders, changing values, trying 0.6, 0.7, 0.8. No, they just set the system running, and it trains the two LoRas, it tries to combine them using this iterative learning approach of ZipLoRA, and then it spits out the results. So I think that's the dream, and it's really cool that, yeah, people are already working on implementations. I encourage you to go try it out. Also go fiddle around with the notebook that I've shared. It's very much, this is just only for illustration purposes. I've probably made some mistakes, but I hope you enjoyed this. This was just me basically diving into a new technique that I'm excited about. Congrats to the authors for a great paper, and thank you for your collaboration as I quickly threw this together over Thanksgiving. And yeah, we'll see where the community takes this in the coming weeks. Thanks for watching.